you'll remember that yesterday we finished by starting to think about how to analyze the motion of a particle that is accelerating. And the important point, of course, is that we cannot have that particle sitting at rest in a frame of reference, because that would make the frame of reference accelerate, and then it would not be an inertial frame. But what we can do is we can imagine that at any moment that particle has a specific velocity, and at that moment it has a momentary and instantaneous rest frame. A moment later, that rest frame is left behind and the particle's accelerating away, but just for that moment there is what we call an instantaneous rest frame. And that will help us to work out how to describe the acceleration in terms of some background frame that we're not even, is maybe never at rest with respect to the particle. Okay. So the situation is the usual one, that we've got, we've lined things up as usual so that the particle's moving along the x-axis, and we've got our usual two frames of reference, and the particle, I always get these numbers muddled up, so I'll have to check. The velocity of the instantaneous, so this is instantaneous rest frame, we imagine that that's, we call that, it's got velocity v1 with respect to s, and so v1 is a constant velocity. It's just the velocity that the particle has at one moment. The particle here is moving with respect to s at v2, and it's with respect to s dashed, it's moving at v2, and it's moving at v with respect to s. v2, so this is a constant, and this is not constant. And we're going to do the usual thing. We're going to use the Lorentz transform and fiddle about, and we'll get a description for the acceleration of this particle in terms of this frame of reference. But this instantaneous rest frame will be an intermediary for us to do the calculation. I should also write up those identities which I wrote up yesterday. I'll put them up again because we're going to need them. Gamma v is the same as c root gamma squared minus 1, c squared, c squared d gamma, that's the derivative, is equal to gamma cubed v dv, that's the derivative. And the derivative of the product gamma v is gamma cubed times dv. Turns out those are going to be they're all very easy to discover. Maybe you've already done it, but we do need them. So in this instant, at this instant, the addition of velocities gives us that the velocity v of the particle with respect to s is v1 plus v2 over 1 plus v1 v2 over c squared. That's the addition of velocities that we discovered before. When we first derived this, everything here was constant, okay? But now we're thinking of this one is constant, here and here, and of course c is constant, and of course 1 is constant, but the others are variables. So now we do some calculation. I'm afraid it's just sort of elementary calculus, actually, and I'm not going to do all of the details. I'll miss some out and ask you to complete the details, but If you can't, then please catch me when I'm trying to eat my dinner or breakfast or something, or tomorrow in the lecture, and I can help you. Okay. I don't think I'm going to miss anything out that's really difficult. That's not my intention anyway. So first of all, we differentiate v with respect to v2. Okay, they're the two variables here. We differentiate this expression with respect to v2. And it turns out that we get this expression. Let me just think how to write this. I'm not going to write it as it is in my notes. Give me a moment here. So it turns out it's 1 minus v1 squared over c squared over 1 plus v1 v2 over c squared squared. Have I done that right? Yeah. So there's a little bit of algebra involved in this, but it's just elementary stuff. You differentiate this expression with respect to that variable. v1 is constant, and simplify, and you get this. And we can write this in this form. This is the gamma function for v1. It's the reciprocal of the square of the gamma function. In other words, it's gamma to the minus 2, but where the velocity used in the gamma is v1. So I'm going to, you see, whenever I've written gamma before, I've always just written this for some velocity v. So gamma depends on v, and I've always hidden that before. And now I mustn't hide it because I'm going to have different gammas. So I'm going to have, this is gamma of v, is that, okay? So gamma of v1 is that. So I'm going to use that expression because I'm also going to have gamma of v2 and gamma of the original v as well. So this is gamma of v1 to the power minus 2 over 1 plus v1 v2 over c squared squared. So that's not difficult. Another, again, not difficult expression is that gamma to the minus 2 of v turns out to be this. It's gamma to the minus 2 of v1 times gamma to the minus 2 of v2 over this same expression. So again, this is an equation which I'm asking you to check. So this is 1 minus v squared over c squared, okay? And instead of v squared, you square this and do some algebra, and you get this. So it's not obvious, but it's easy to do the algebra. Okay? And now you see why I really need to keep saying, when I write down the gamma, gamma of what? And so these brackets, this is the gamma factor for the velocity v1, this is the gamma factor for the velocity v2, and so on. So putting these two together, we have therefore dv dv2 is gamma to the minus 2 of v over gamma to the minus 2 of v2. If you look at this expression and this expression, this comes out. It doesn't go on forever, this calculation, I promise, but we do have a few more steps to do. So now we're going to focus on this particular moment when the velocity of the particle with respect to this frame is 0. In other words, that's the moment when this was the rest frame. So when v2 equals 0, then this expression, if v2 is 0, then this is just 1. Okay, and so this expression becomes dv2 is gamma to the minus 2 of v, or in other words, dv is gamma to the minus 2 of v times dv2. Good. We'll come back to that in a moment. Now, at that same instant, when v2 is 0, there's a time dilation between these two frames of reference, which we calculated yesterday. And so the time dilation is this. It's dt dashed is dt over gamma of v1. If you just check back in your notes for the time dilation from yesterday, you'll see that it's this. And where the relative velocity of the two frames is v1, and so it's just, that's the gamma factor for v1. So that's the time dilation. Good, and we'll come back to that in a minute too. Now at last we define the proper acceleration. Is the acceleration of the particle in its instantaneous rest frame. So if you want to calculate the acceleration, if the particle wants to calculate its acceleration, what it does naturally is it says, at this moment I've got a rest frame, and in that rest frame I calculate my acceleration. What else could it do, really? So that's what the proper acceleration is. So the proper acceleration must be the velocity that the particle measures with respect to its instantaneous rest frame, dv2 by dt dashed. That's the time that's ticking in the instantaneous rest frame. And that I'm going to, and I think it's a fairly common symbol, I don't know why, we're going to call that alpha. That's the proper acceleration, alpha. Is dv2 dt primed. But now if we look at these two expressions here, I've got dv2 in terms of dv, and I've got dt primed in terms of dt. And that's good because t is the time ticking here, and v is the velocity of the particle with respect to this frame of reference. So I can relate the proper acceleration to dv dt. And if you just look at those two expressions, you'll see that you get a gamma cubed of v dv dt. So all I've done is I've substituted for dv2 and for dt primed using those two, and it turns out you get this. I've also used the fact, you may not have, that at that moment v1 is the same as v. Okay, so this is the same as gamma of v, and that's why you get a gamma of v here, and you get two of them here, and that's where you get the cube over there. And then I use one of those identities over there, or maybe two of them. I can't remember, maybe it's just one of them. And you can see that this is the same as d by dt of v gamma of v. So I must be using this one. I'm using this one. Okay. So that's my expression for the proper acceleration. It's a very nice expression. It's in terms of things that S knows about, right? So now what we're going to do is we're going to look at a special example, right? So a particular example. There's no reason why the proper acceleration has to be constant. So alpha could, in general, vary. A particle might have some acceleration at some time and then a different acceleration at some other time, of course. But in our next example, we're going to assume that as a special case, we're going to study the case where alpha is constant. So a particular example, alpha is constant. So when you write your notes, please don't just write alpha is constant, because it doesn't have to be. But we're choosing to study the case when it is constant. Okay? And then we can actually integrate. We can do some integrals. We've got this equation here. We've got d by dt of v gamma is alpha, which is constant in our example. And so we can integrate and we get so v gamma must be alpha t, right? If we make a choice of initial condition, I'm choosing t equals 0, and I'm choosing that the velocity is 0 when the time is 0, okay? Which simplifies to the algebra and is a sort of easy case, right? And then you make v the subject of this equation. This is just a function of v, remember? So make v the subject of this equation by doing some algebra, and you get this. So v is nothing but dx dt. And from this equation, if you manipulate it, you get that it's c alpha t over the square root of, have I looked at the correct equation here? C squared plus alpha squared, yes. So if you make v the subject of this equation, you get this. And that's dx dt. And we can integrate again now. Okay, turns out this is an elementary integral. And if we integrate again, it turns out that we get x squared minus c squared t squared equals c to the 4th over alpha squared. And I think again I've ignored the constant of integration. I've just thrown it away because I can always adjust later on if I need to. And this is very nice, okay? This is what the particle is doing if it's experiencing constant acceleration. And as you can see, it's a hyperbola in space-time. Okay, it's a hyperbola. So if we drew a space-time picture, it would, which I'll put down here, it would look something like this. So it would be some hyperbola like that. That's your constant acceleration curve. So this is the world line of the particle. This is the frame S. This is t, or maybe it's ct probably, and this is x. So that's what constant acceleration looks like. And because it's a hyperbola, it's called hyperbolic motion. Okay, good. Right, so I'm actually going to be doing, I might not do all of the details, but I'll do quite a lot of this exercise. It's exercise 24 in the lecture notes. And I don't want to write it all down because it's quite a lot of writing. So I'm hoping that you've got, have people got the lecture notes now? Good, okay. Has anybody had difficulty finding my lecture notes? No? Everybody's got them. Good, okay, then I don't need to write every word down. So the exercise basically, first of all, it says that if we're using units of years and light years, which is a natural thing to do, in those units, g, the acceleration due to gravity, is something like it. Did I? I've got it over there in my other notes. It's something like 1.04 ... So it's basically 1, which is quite nice. Okay, in the natural units for space-time, the acceleration that we're familiar with, because here we are experiencing it, is just a tiny bit more than 1. So what we're going to do is we're going to imagine that a spaceship leaves from the solar system. I know that the solar system has a gravitational field and we're pretending that there isn't one, but let's not argue about that, please. So the spaceship leaves the solar system and heads off towards something, and it doesn't change its direction, it just chooses somewhere and goes for it, and it chooses to fly at a constant acceleration of 1, okay, which is very nice for the algebra. Okay, so the alpha is going to be 1, and it's also very nice for the people in the spaceship because they're experiencing an acceleration which is just a little bit less than what we're used to here. Okay, so that's very comfortable for the people in the spaceship, and that's what it goes off with that constant velocity. Sorry, with that constant acceleration. So I'll abbreviate the exercise. We've got a spaceship with alpha equals 1, constant acceleration 1. And it starts from rest here and off it goes. Maybe we can persuade Ali Nessin to build a spaceship and send it, okay? Okay, so the first part of the exercise is show that its Lorentz factor is given by cosh, the hyperbolic cosine of tau, where tau is the time measured in the spaceship. All right, so that's the first thing we have to do, show that gamma is the hyperbolic cosine of the spaceship time. Know that the time dilation gives us this. Right, that's time dilation on the in the instantaneous frame of the spaceship. And we know from here, this expression here, that's 1, and we've got 1 is equal to gamma cubed dv dt, and therefore dv is dt over gamma cubed. And if we put those two together, we find that gamma squared dv equals d tau. Gamma squared dv is the same as d tau. And now we use these things and we get that therefore c d gamma over root gamma squared minus 1 is d tau. Whoa, so that must be using this one and the relationship between dv and d gamma, this one. So if we use both of those, we get this. Okay. And now I'm pretty sure now we integrate. Yeah, so in these units, c is equal to 1. In these units. And now we can integrate that, and we get that gamma is the hyperbolic cosine of tau. Good, at last I got there. Okay. And now the exercise goes on to get you to write down the value of gamma for various values of the elapsed time tau. And so the question goes on to say, suppose the onboard clock, the clock in the spaceship, measures 1 day. In other words, tau is 1 over 365, because tau is measured in years. Then what's the gamma factor? Well, if you ask a machine, it tells you that gamma is 1 point, crikey, how many zeros? 1, 2, 3, 4, 5, I think. 1, 2, 3, 4, yeah. 1, 2, 3, 4, 5, 3, 8, right? So after a day, the gamma factor has hardly changed. So you're accelerating at 1g, right? And after a day, not much has happened. After a year, so tau is now 1. The gamma factor has now changed. It comes to 1.5, so still not huge. 1.5431. What about if you fly for 10 years? So it's a big spaceship, very comfortable, lots of food. Then the gamma factor is quite big. It's 11,013. So after 10 years, you've really begun to affect the gamma factor in a big way. Okay, now that's exercise 24. Now for 25, it's the same spaceship, same setup. I just divided it into 2 exercises because each one is quite big. Find expressions for v and x in terms of t. That's the frame of reference here, right? We're the people who stayed at home and watched the spaceship go away. And hence calculate the distances and times travelled according to us by the spaceship for these different values of the time experienced on board the spaceship. So that's what's happening on board the spaceship. What do we think's happening? Okay, so that's the exercise, and there's a bit more which I'll write down in a minute. And now we write down the equations that I started to write down a few minutes ago. Namely, we want to find v in terms of t. Here is v in terms of t, and all we need to do is to put c and alpha both equal to 1, and we get v equals t over root 1 plus t squared. And we integrate that. V is dx dt, so x must be root 1 plus t squared minus 1. And of course the quickest way to do that now is to differentiate this, and you discover that you get that. Now this equation here, if you look back, which one? Gamma is, yeah, so you look back to this equation, right? So we've got an expression for v over there. We know that alpha's 1, and if you put those in, you get that gamma must be just the square root of t squared plus 1. So it's t over v. So if you divide t by this expression, then you get that. And therefore, looking at those two, in fact, so x is gamma minus 1, and t is, Well, you just make t the subject of this equation, and it's the square root of gamma squared minus 1. Okay, so we found v and x in terms of t and also in terms of gamma. And that's good because we know what gamma is. We've got it here. And so the question is now, what are these numbers after this time has elapsed in the spaceship? So what's x? So I'll complete this table. So x, it turns out, so the distance that we have seen the spaceship travel is not very much. It's going to be this minus 1, so it's going to be 0.000038 of a light year, remember? X is measured in light years. After 1 year on board the spaceship, x is just this minus 1, so it's so it's half a light year, which is quite a long way, but the nearest star is 4 light years, so, you know. But after 10 years on board the spaceship, suddenly you've moved quite a long way. X is 1 less than this light years, so it's a long way, right? It's actually started really, you've moved a long way now. Well, not in terms of the galaxy, but in terms of the solar system, you've moved a long way. What about t? That's the time elapsed here while the spaceship was doing all these things. So after 1 day on board, the time here is 0.00275, how many decimal places? 68 of a light year, of a year. I don't know what that is actually. After 1 year on board, the time here is more than a year, 1.175 and some change. After 10 years on the spaceship, the time here is basically the same as that number. It's a long time, right? They're living, their clocks are slowing down a lot, so they think 10 years has elapsed. We think 11,000 years has elapsed, right? Long time. So now what you imagine is that you've sent this spaceship off and it accelerates away at 1g, and the people on board experience 10 years, and after that the spaceship turns around and stays accelerating at 1g, but now towards us. And of course the whole thing works again, except everything is just the other way around. It's coming towards us. And it does that for another 10 years on board. And at that point, it's stationary with respect to us. Long way away and stationary with respect to us. So then, of course, it accelerates back towards us for 10 years on board, and then turns around and decelerates, so that after another 10 years on board, it's arrived back here in the mathematical village at rest, okay? And 40 years on the spaceship, which is quite a long time on a spaceship, but survivable, presumably, but 44,000 years, right? That's a huge difference. Actually, it occurs to me that what we should do, I haven't done it, I thought about it just as I was walking over here. We should try and work out, I'm sure you can do it. The nearest star is 4 light years away, so you could ask what these figures are if you wanted the spaceship, which it's called Alpha Centauri. So how long would it take if the spaceship were going to Alpha Centauri and back? How long would the people on board the spaceship experience? And how much time would it take from our point of view? And it's much less. It's not as bad as this. 10 years is quite a long time. OK, so I've left quite a lot of detail for you to check. This was really a an exercise, well, it was a practice exercise in dealing with acceleration, but it also demonstrates how once you get up to a reasonable speed, which this spaceship does after some years, then the time dilation effect really begins to count a lot.